Yes, before going to comparisons, let's first talk about these four heterocyclics. We want to see how the heteroatoms interact with the carbon atoms. So we are going to talk about the Pyrrole, pyridine, Furan, and Thiophene. Please don't forget to subscribe, like the videos, and share. Let's go. Pyrrole, this is the structure. This is its structure. This is Pyrrole. Then pyridine, it is this. Then we have Furan. This is the structure. And Thiophene. So those are the heterocyclics we have. But for Pyrrole, the heteroatom is nitrogen, and pyridine, the heteroatom is nitrogen. But we want to see how do they interact with the carbon atoms. Why are they different? So nitrogen, its atomic number is 7 for nitrogen. Means that its electron configuration is 1s2, 2s2, then 2p3. That is nitrogen. So at the ground state, we shall have this 1s. This is 1s2. Then we have 2s2. This is 2s2. And we have 2p2, having 3 electrons. The same. So at excitation, this one will remain with 2 electrons. Then here, 1 electron will shift to the 2p orbital. So we shall have this. We shall have 1 electron remaining at the 2s. Then we have this. So this is the 2. This is the p orbital. So for hybridization, it will now depend, because here we have nitrogen hybridizing to react with these carbon atoms, and here we have nitrogen. But how do they differ? Now for here, remember the number of pi electrons follows this formula. It's 4n plus 2. These are the number of pi electrons. So we said if n is 0, we shall have 2. If n is 1, we shall have 6. If n is 2, we shall have 10. So if this carbon is contributing a pi electron, here we have 1 electron, here we have another electron, then here and here. So we have 1, 2, 3, 4 electrons, meaning that for this nitrogen, it should contribute 2 electrons to make 6. If it contributes 1, we shall have 5 pi electrons, which are out of the electrons we are looking for. Yet this structure is aromatic. We said it is aromatic. And for aromatic, they should satisfy this criteria of the Hackworth's rule. So this nitrogen should contribute 2 electrons. Let's see. If it is to contribute 2 electrons for the resonance system, here we shall have this. So hybridization will take place, meaning that if it contributes 2 pi electrons, these electrons, the 2 electrons it contributes, will be unhybridized. They will be unhybridized. So we shall have the hybridized electrons will be 3. We shall have 3. So remember, this is sp2. So it should be sp2. 2 electrons from the p orbital and 1 electron from the s orbital. And we shall have these electrons remain unhybridized. This is the hybridized orbital. This is unhybridized. So if we are taking these ones, like these two, we would have remained with 1 unhybridized electron. This one would be sp2, but 1 electron is unhybridized. If it is 1, we wouldn't make 6 electrons for the resonance or for the pi. So mean that it is these electrons which remain, these lone pairs of electrons, they are the ones which remain unhybridized. So that's why for Pyrrole it's done like this. Then we put 2 electrons inside, showing that they participate in resonance. So this is Pyrrole. Now, when it comes to pyridine, it's the same atom, nitrogen, which is 7. We shall have same ground state, excitation state. Now, at hybridization for the pyridine, it will be this. This is the 1s2. This one. Now here, since we have 1, 2, 3, 4, 5, we have 5 pi, we have 5 electrons, unhybridized p electrons or p orbitals. Mean that nitrogen will contribute only 1 electron. So we shall have this. We shall have this one from the S will be here. Then we have this one. These 2 lone pairs of electrons, they are also hybridized. And we have this. Then only 1 which remains unhybridized. So this is the sp orbital, the hybridized orbital. And this is the p unhybridized, but here it is the sp, this is the p. In p we have only 1 electron. The lone pair is also hybridized. It is in sp. This is the hybridized, and this is the unhybridized. So nitrogen will contribute only 1 electron. So this electron is the one which contributes to the resonance. And these ones, they will be outside because they don't participate in resonance. They are sp. Remember the p, if this is the structure, this is the nitrogen. Remember the carbon has 1, even this carbon has, also this carbon has an hybridized p electron or orbital. So this nitrogen will contribute only 1. So we can have this. So these ones, the 2, they will remain outside like this. That's why we draw them. We draw the structure like this, then we put lone pairs outside because they are sp. They are not p hybridized. They are in this form. So watch those videos about hybridization and molecular geometry. Please check them such that you see very well how does the hybridization occur and also the structures of the electrons. So for pyridine, nitrogen contributes 1, but for Pyrrole it contributes 2, such that it maintains the aromaticity. The aim is to maintain aromaticity. This one, to be aromatic, should contribute 1 electron so that it will make 6 pi electrons using the formula, which is 4n plus 2. This one contributes to maintain aromaticity. So that's how they differ. Now let's go to furan. Then for furan, oxygen has 80 electrons. This is its electron configuration. So this is its atomic number. Its electron configuration will be 1s2, 2s2, 2p4. This is its electron configuration. So we shall have at ground state, have this. Then you have 2s2. Then we have this, the 2p4. So excitation shall have this. These ones remain. Then 1 electron will go to p orbital. So we shall have only 1 electron here, other 2s. At 2p, we shall have these electrons. Then 1 shifted, it's here. Then we have this one. So since we have 1, 2, 3, 4, oxygen should contribute 2 electrons for resonance to make 6. So at hybridization, we have this. So we should have 2 unhybridized electrons, and it should be sp2 hybridized. So we have the sp2 shall have this. This is the S, and we shall have the lone pairs hybridized, then 1 electron, which is also there are 2 electrons and a lone pair, and we have this lone pair unhybridized. So these ones will contribute to the resonance. So we shall have this is unhybridized. This is the hybridized orbital. So why like this? These ones, this and this, they form these bonds. Yeah, this and this, they form the bonds. Then this one will be outside. Then this unhybridized lone pair will be inside, like that. So this is the structure of furan. This is its structure. So it will be like this. So if this carbon is having this unhybridized electron, and this one, and this one, oxygen should contribute 2. So to have this and this one. This one can form a bond like this, then this one with this one, this one with this one. So these 2 lone pairs, they will participate in resonance, and they are perpendicular to the plane. Oxygen and these carbons, they are on the plane, but these unhybridized electrons. The unhybridized electrons, they are perpendicular to the plane. And also here, this one, this one, this one, this one, and these two, they are perpendicular. So such that they form the electron cloud up and down. So that is Furan. This is the p orbital. This is the s, and this is one s. When we go to Thiophene, s, its atomic number is 16. If it is 16, its electron configuration will be 1s2, 2s2, 2p6, then 3s2, and 3p4. So that's it. Meaning that we shall have at the ground state, we have 1s. Then we have 2s, and we have 2p. At 2p, they are all full. It is full. Then we have 3s and 3p. Excitation. We shall have this one remaining. Then this one as well. Also this one. Then one electron will go to the 3p. So we shall have one electron remaining here. Then here we have this. We have this. Then for hybridization to occur, we have here one p orbital, p electron, here also one, one, one. So we have 1, 2, 3, 4. Mean that s should contribute also to unhybridized electrons. So mean that this one will remain. Then we have this one also remaining. This is 1s, 2s2, then 2s, then 2p. This is 3s, this is 3p. Remember, for the carbon atoms, they have 2p unhybridized electron. It is in 2p orbital. But here, for the s, we shall have in 3p. They are in the third energy level. But for the carbon atoms, they stop in the second energy level. But let's see. These ones also remain. Then sulfur, here we have 4 electrons. Sulfur should contribute 2 electrons, meaning that we shall have one of the lone pair remain unhybridized. Then we have these. We have the 3s, then we have one lone pair, then one electron. So it is sp2 hybridized, 1s, then 2 from the p orbital. We have 1 orbital from s and 2 orbitals from the p. Then 1 remaining p orbital with a lone pair. This is unhybridized. This is the hybridized. We are going to see. We have seen that oxygen contributes also 2 and remains with 2. But what it contributes, they are in the P, in the 2, in the second energy level. But for the sulfur, it contributes also 2, but they are in the third energy level. But remember, for the carbon, they are all in second energy level. So we are going to see how does that affect the ring stability. We are going to see that here, the comparisons. That's why I wanted to show you this. So mean that also sulfur will have 2 electrons, these ones, participating in resonance, and it has lone pairs outside, like furan. Then these ones, these ones which form the bonds with the carbon, the sigma bonds. These ones, they form the sigma bonds. Then this one will contribute to the pi bonds. So mean that we shall form a total of 6 such that it is aromatic, such that it maintains the aromaticity. Now we are good to go. Let's go to the comparisons and see how do the interactions of the heteroatoms with the carbon atoms affect the electron distribution or electron density and all these others.